Welcome to another episode of Cuda Education. Today we are moving on to the next algorithm in the sample set. So we are on compute n body, right? And just to get the party started, let us just see what that is all about, as we could see here. Okay, so I'll just let this run in the corner um, while we investigate what's going on. Okay, so compute shader and body simulation using two passes and shared compute shader memory. This sample shows how to combine compute and graphics for doing n-body particle simulations. It calculates a particle system movement using two separate compute passes, calculating particle positions and integrating particles. For that, a shader storage buffer is used, which is then used as a vertex buffer for drawing the particle system with a graphics pipeline. To optimize performance, the compute shaders use shared memory. Okay, so this is the party right here, as you guys can see. Um, I do want to, basically, so this is the main file. It is about 700 lines of code, and we do have, you know, particle.frag shader, particle.vert shader, um, particlecalculate.comp shader, and particleintegrate.comp shader, right? Um, you know, the thing is that we're making our way through all of the examples. I've actually started to take a liking to compute, strangely enough. I had a huge aversion to compute just in general because Vulkan is a graphics thing and we want to see pixels on the screen and all that stuff. But um, you know, in a lot of ways, compute drives a lot of things, right? Um, and it's wise to get comfortable with compute stuff. This particular algorithm has a lot going on. So we have compute stuff, heavy compute stuff, and then we have to transfer all that computation to the graphic stuff so that we could see stuff on the screen, like we're seeing here. Obviously, once we start talking about this stuff, we're talking about synchronization. That's going to be a thing. Um, yeah, there's a lot. Two pipelines because you have the calculate particle positions and the integrating particles pipeline, and then on the compute side, so two pipelines on the compute side, and then you have the graphics pipeline to actually display the stuff that's going on that we want to see on the screen. Um, Memory barriers, pipeline barriers, semaphores, fences. Um, you know, we're gonna have to do Q family stuff. Um, this particular algorithm, based on my revision, it does try to put the compute workloads onto the dedicated compute queue. Now, in previous episodes, in the GPU hardware review episode, we did talk about the fact that there is a main queue family that you could have several lanes of simultaneous work that can do graphics and compute, right? So that's like sort of the main queue family that sort of everything gets done on, right? But then you also have a dedicated compute queue family that basically only does compute, right? So the hustle here is um, instead of putting the major compute workload on the main queue family that also can do graphics, the hustle is to put the graphics stuff on the graphics queue family, the main queue family, and then put the compute stuff on the dedicated compute queue family, right? Um, it's a blessing and a curse. The blessing is that you separate out your graphics tasks from your compute tasks, and you have the opportunity to have parallelism, right? So remember, these queue families sort of mimic what hardware you have on your particular machine. So assuming, for my machine, I'm an RTX 4050 laptop, right? GPU, NVIDIA. Um, there's the main graphics and compute queue, and then the compute queue. So you do the compute on the dedicated compute queue, and then you do the graphics stuff on the graphics queue. But then the problem is that you have to synchronize, because at some point, one has to communicate with the other to see where they're at, to push values, to make sure everything is in sync, is lined up, all of that stuff. But it's still a better situation than having compute and graphics on the same queue family and all of that stuff, right? So we're gonna kind of see that here, um, in a strange sort of way. We're not doing a deep dive at all. I'm just kind of running through the code. It's 700 lines of code. So this example is gonna hold us for a good little while, but I think it's actually, I mean, I know it's in alphabetical order, but it's a good follow up to the compute headless example, because we kind of get into a little bit more complicated stuff. Um, namely the multiple passes on the compute side, which is something we haven't seen before. Um, and then basically, yeah, just a lot of stuff like that. Okay. So yeah, let's just dive into it as the first video, and we have a lot of work ahead of us. All right, so first thing, we decide whether how many particles are we gonna have in the simulator. If it's an Android device, we tone it down a little bit. For my machine, we get a multiple of 4 of 1024. Okay. Um, Also, thing to note is that when I run this example on the integrated graphics card, I get about 100 FPS. On this NVIDIA graphics card, I get 119, 120 FPS. Just a side note, right? I didn't realize that my integrated graphics card could run Vulkan, because on my other machine, the integrated graphics card could not run Vulkan. So, um, yeah. But anyway, so right, so we have the 4x for this. Um, Vulkan example base. So we have. I'll just compress this a little bit more, just so we have a little bit more space. Actually, I'll get rid of. Well, I'll just leave this here. Actually, and I'll actually increase this text size. Okay, so you guys can really see the text. Okay. All right, so we have textures, we have particle definition, which is position and mass, and velocity and gradient texture position. Um, yeah, number of particles. Use a shader storage buffer object to store the particles. This is updated by the compute pipeline and displayed as a vertex buffer by the graphics pipeline. So again, guys, there's compute and graphics stuff that we have to contend with, right? Resources for the graphics part of the example. So we have the graphics stuff. Used to check if compute and graphics family queues differ and require additional barriers, right? This is, this sample is intended to run on many machines, so many different GPUs, older GPUs, newer GPUs, and everything in between, right? Different brands, different vendors, all that. So you have to see if the compute and graphics queue are separate queues or the same queue. And if they're separate queues, you have to do barriers, right? Because if it's the same queue, you could kind of get, I guess, implicit synchronization. But if not, then you don't. Particle system rendering, shader, binding layout, descriptor set layout, right? Yeah, we're gonna have to clean up a lot of minor stuff too with this example. Get it very clear. Descriptor sets, particle system rendering, shader, bindings. Particle system rendering, shader, bindings, right? Pipeline layout, layout of the graphics pipeline, pipeline, particle rendering pipeline. Uniform data projection, view, screen dim, unit. This is usually camera stuff. Um, Uniform buffer, scene, matrices. This is all part of the graphics conversation. Resources for graphics part of the example. Right, so this is all graphic stuff. Resources for compute part of the example. So we have queue family again. We have to check if the compute is same or different queue family. Um, Separate queue for compute commands. Queue family may differ from one used for graphics, right? Command pool, command buffers, descriptor set layout, descriptor sets. Here in the compute side, we also have fences. Okay, fences to make sure command buffers are done. So remember, fences is CPU to GPU. So the CPU submits the command buffers, and once the GPU has done all the instructions in the command buffer, we have to signal back to the CPU that the instructions are done. Compute semaphores. Okay, ready and complete. Okay, so now we get into semaphores. Semaphores is GPU synchronization, right? So you have two processes running on the GPU, and you need to make sure that those two processes run in order, and you have a status for, when stuff is ready and when stuff is complete. So that's our compute semaphores, right? Um, Uh, yeah. Pipeline layout, layout of compute pipeline, pipeline calculates, compute pipeline for n-body velocity calculation, pipeline integrate, compute pipeline for Euler integration, second pass. All right, so we have the first pass and the second pass. First time we're seeing this, guys, first time we're seeing this where we're doing a first pass and a second pass. In this instance, it's pipeline wise. So we actually have two pipelines that we have to contend with. Vulkan is the gift that keeps on giving. So yeah, we have to contend with two pipelines on the compute side because we're doing two different things. Um, and I also feel that's why we have two compute shaders, right? One for the calculate and one for the integrate. Okay, so it's part of. I'm sure everything could have been done on one run, and everything could have been done in one shader, but for semantics and just organization and sanity, we break things apart. Okay, um, uniform data parameters used to control the behavior of the particle system. Um, Also, guys, just so you know, as it relates to CPU side going to GPU side, the shaders, CPU to shaders, transferring information from the CPU side to the shaders, we do use our specialization constant. So you guys know that in the previous episode, um, for Vulkan, the previous two episodes, but especially the previous episode for Vulkan, we hammered away at specialization constants, which is a sneaky way of getting information from the CPU side over to the over to the shaders um, efficiently, if you will. Okay, so we're gonna see that quickly here. Let us continue. So we have uniform, camera stuff. We have these structures, which we're not going to get into right now. Um, we're loading assets. So we have textures. Okay, so textures we're loading. Set up and fill the compute shader storage buffers containing the particles. Yeah, so we'll have to get into this stuff. Number of particles. Um, yeah, so this is particle related stuff. Um, First particling group has heavy center of gravity. So if I comment this stuff out, the sheer the initial run of the particle system, changes the sort of order of how it goes about doing its stuff. Um, yeah. So yeah, that's just for the first set of particles for the first particle, and then everything else it follows these instructions. Color gradient. If I comment this out, we just get one color for all the particles, right? But we do want a color gradient so it looks more attractive. Storage buffer size. Um, SSBO won't be changed on host after upload, so copy to device local. So this is staging buffer stuff. We have a transfer buffer. Then we have the vertex buffer. The SSBO will be used as a storage buffer for the compute pipeline and as a vertex buffer in the graphics pipeline, right? So notice that we have vertex buffer, storage buffer, transfer, and device local. These are the different flags for what the buffer is or can do and all that stuff. Um, Copy from staging buffer to storage buffer. Um, I'm not going to spend too much time on this, but I will do some due diligence on it because I can't just keep ignoring transfer buffer operations. It's actually pretty important. But basically, we're moving stuff from CPU side to the GPU, right? Execute a transfer barrier to the compute queue if necessary. Okay, so this now gets into um, remember we said that we have the graphics queue, which can also do compute, and then the compute queue. Um, if we're offloading to compute and the graphics queue is different from the compute queue, we're gonna have to we're gonna have to we're gonna have to put some synchronization between the two of them. Um, Basically a pipeline barrier, right? Now this is as I've said before, this is a heavy synchronization barrier, but it is necessary because we can't have compute running way ahead of graphics and vice versa. Because they're running on different threads, different situations. So we have notice that we have this VK access vertex attribute read bit, right? So we have to make sure that whenever we're reading stuff, um, that we're not also trying to write at the same time. All that synchronization stuff, right? If we're reading vertex information, compute can be actively trying to manipulate the vertex data also and all this stuff, right? And vice versa. Um, Um, yeah, so we'll have to get into this, but this is a huge, synchronization um, thing that we're gonna have to contend with. Vertex input bits and stage bottom of pipe bits. I think I've seen this somewhere before, but we'll have to dive into this a little bit more. Um, yeah. Okay. Right. So prepare descriptor pool. You remember, guys, descriptors are sort of assets in memory that this is shared between graphics and compute, right? So we have stuff in memory, but we can't just give Vulkan a blank USB drive. We have to actually describe what's in memory and how it can be used and the types and all that stuff, right? So we have uniform buffer, storage buffer, and image sampler. Um, and then we do some descriptor pool stuff related to that. Prepare graphics, um, vertex shader, uniform block. Again, notice that the buffer stuff is uniform buffer, host visible, host coherent. Um, we get into descriptor layout, image sampler, fragment bit. The shader stage is a fragment. Makes sense. The uniform buffer is a vertex piece of it. Um, what is this doing now? Sets per frame, just like the buffers themselves. More descriptor stuff per frame, I guess. Right. So again, descriptors is just describing assets in memory that we have to contend with. Pipeline layout. Yeah. Now this is where things get involved. So we're doing pipeline stuff, input assembly, rasterization state, blend attachment state, color blend state, depth stencil state, viewport state, multi-sample state, dynamic state, enables dynamic state, shader stage. Right. This is on the graphics side, right? So it's just one pipeline, vertex input state. It's just one pipeline that we're doing on the graphics side. Input attributes, vertex input state, shaders. So this is a spare V of the compiled vertex shader and fragment shader, right? So remember we have to compile our shaders. So it's just pointing to the spare V file after we compile these things to spare V. Um, and then we actually create the pipeline. A lot of stuff going on the pipeline, right? A lot of things have to be boiled down into it. Additive blending, and then we do VK create graphics pipeline. Okay, so that's our graphics pipeline here. We do all of this work up here just so we could get our graphics pipeline, right? And we could run lowercase VK create graphics pipeline. Vulkan is a gift that keeps on giving, guys. And then we do the same thing for compute, but here now we're gonna have two pipelines. Create a compute capable device queue. The Vulkan device create logical device functions, finds a compute capable queue, and prefers queue families that only support compute. right? So this is where we're talking about, we want a dedicated compute queue. For my GPU, we do have a dedicated compute queue. Depending on the implementation, this may result in different queue family indices for graphics and computes, requiring proper synchronization. See memory barriers in build compute command buffer, right? So we looked at the memory barrier, and VK get device queue, device compute family queue, blah blah blah. We'll have to investigate this because, like, what I'm interested in is how does the code enforce that we want the compute queue with graphics only. I mean, with compute only, aka it doesn't have graphics. So we want the queue family with graphics, with compute only. We want the queue family with compute only and doesn't have graphics. But how does it go about enforcing it? I know in previous examples there was like an if statement, or in sort of my example, like I modified some code and there was an if statement to say not graphics, right? But we'll have to dive into that. Compute shader, uniform buffer block. All right. So what are the flags that we're using for this buffer? Uniform buffer, host visible, host coherent. Okay. Create compute pipeline. Compute pipelines are created separate from graphics pipelines, even if they use the same queue, right? Binding zero particle position. Um, Binding one uniform buffer. So the particle position storage buffer is type storage buffer, and uniform buffer is type uniform buffer. Um, descriptor layout. Descriptor layout. Okay, so we got descriptor layout for compute. Right, so uniform. So for each uniform buffer, we have a descriptor set stuff to do with that. Um, yeah, VK updates, descriptor sets. So we'll have to dive into this also. Binding zero again, and then binding one. I guess here you're initializing, and then you do it for each uniform buffer item. Create pipelines. Okay, so we have boilerplate stuff. All right, so this is where we get into the two pipelines here. So the first pass, particle calculate comp SPV. So the particle calculate, that's this shader right here. Shader stage compute bits, right? We want to use as much memory shared. We want to use as much shared memory for the compute shader invocations as available. So we calculate it based on the device limits and pass it to the shader via specialization constants. So here's where specialization constants come into play. Um, Based on the device limits and pass it to the shader, right? So we'll have to get into that, guys. This is the first pass. VK create compute pipelines, right? So we create a pipeline for pipeline calculate, right? And then we do a second pass, similar pattern, right? Pipeline into particle integrate, right? And we do the same thing again, pipeline integrate. Yeah, we have to remember, guys. This code is supposed to be run on many different environments. So some of the complication that we see here is just because the author is trying to manage, different scenarios, right? So that's why all of this stuff is necessary. Um, Create command buffers for compute operations. Fences to check for command buffer completion. Okay, so we're pretty familiar with fences, right, guys? The CPU side submits the command instructions to the GPU, and then the GPU signals that it's complete, and you know the CPU gets back control and all that stuff, right? Semaphores to order compute and graphics submission. So again, semaphores is compute. I mean, it's GPU stuff. So the compute and graphics stuff is all on the GPU, but you have to make sure that things are done in an orderly fashion. So we have ready and complete. Um, signal first. Use ready semaphore. So initial conditions, all of that stuff. Update compute command buffers, update graphics command. These are just functions, helpful functions. Prepare. We will be using Q family indices to check if graphics and compute Q families differ. If that's the case, we need additional barriers for acquiring and releasing. Yeah, we've said this a million times before, but we actually have to do it for the prepare side. Build graphics command buffer. Yeah. Acquire barrier. Right, so we have a pipeline barrier to acquire, control. This is all under begin command buffer, right? So we acquire control, draw particle system using the update vertex buffer. So then we draw the particle system, begin render pass. Basically do all of our graphic stuff, end render pass, release barrier. Right, so now we're releasing end command buffer. So you see, guys, we have to acquire and release the barrier. Build compute command buffer, same pattern. We have to acquire the barrier. Do a bunch of stuff. Calculate particle movement. That's the first pass. Add memory and barrier to ensure that compute shader has finished writing to the buffer. Transfer ownership if compute. Yeah, transfer. So we have a barrier here. Second pass. Okay, so we acquire here. Hold on. Okay, so yeah, we'll have to figure out what's going on with this first pass and second pass. So we have the first pass here. We do a bunch of operations. And then we have the second pass here, release the barrier. Then we have a render function. Submit compute commands. Wait for rendering finished. Okay, so we submit compute commands. This is all under render function. Submit compute commands. Okay, so notice that we have a fence here. So we have a fence that wait for rendering finished, right? So we have a fence to make sure it's finished, and then we have submit graphics commands. Um, we have semaphore stuff. Okay, so on the graphics side, remember with graphics you process stuff and then you present to screen, right? So you render stuff and present to screen. So the rendering and presentation is all graphics side and it's all GPU side, right? So in order to manage those two things, we have to use semaphores. Remember, semaphores GPU synchronization. Graphics always has the burden of rendering, drawing to the frame, and then presenting the frame to the screen. So you always have this semaphore situation here on the graphics side. Um, on the compute side, basically the instructions are submitted from the CPU side to the GPU, and then we use and then the GPU signals that it's finished and it returns back to the CPU. So for the compute side stuff, we have fences, but internally on the graphics side, we have semaphores because we have to render and complete. Um, and then we submit. Right. So we also have a fence situation with the graphics. We submit, the graphic stuff is done, and then we return control back to the CPU, and that's why we have the fence conversation here. Submit frame, right? And obviously, if I commented out submit frame, I don't think we'll get our render. And that's pretty much it, guys. That's 700 lines of code for you. So did you lose any attention? For you TikTok guys out there, was this a challenge for you? But yeah, guys. So we have our work cut out for us. It's a lot of stuff going on here, a lot of stuff, and we kind of just have to take it one step at a time and figure out what's going on, and increase our understanding of Vulkan. Now, guys, if you want to be able to run this stuff on your machine, you need tutorial number 1 to install the Vulkan SDK, and tutorial number 13 to install all of these examples, including this one. It assumes you have a Windows-based machine with a Vulkan-capable GPU. There's also, this example is not ray tracing, but there's also ray tracing examples. If you want to be able to run the ray tracing stuff, you also have to make sure your GPU is ray tracing capable. This is the algorithm that's um, basically what we're trying to achieve with all this code. Um, but this is Cuda Education. Like, subscribe, tell your friends. If there's anyone artistically inclined in your community, get them involved in this stuff. Um, the world is going digital. GPU programming is going to be very important. Actually like this. However they're doing these particles, it's actually pretty cool. So I really want to learn how they're doing these particles because it actually looks pretty cool. Anyway, guys, thank you for watching. Have a great day.